All right, let's see. I guess I'll start by just reviewing briefly some of the things from last time, or the last couple of times. And then I want to finish the Feynman propagator, and then I want to do the cross-section where E plus E minus goes to mu plus mu minus. So you're saying that I did basically the charge conjugation and the, all right. Let me just very briefly review them then. The idea is that C a dagger of P S n, n being the kind index, is some phase alpha n a dagger PS n conjugate. That's how charge conjugation works. And the corresponding formula for the annihilation operators are alpha n star A PS n C. In other words, you clearly flip the sign. And for the antiparticles, on the other hand, what you have is CA dagger PSN C inverse is alpha NC A dagger of PSN and CA, this is NC, and then N PS NC C inverse is alpha NC star A of PS N. Okay. And what we found was that we, to have locality, we had to have or causality, we had to have alpha NC is alpha N star. And in that case, what we arranged was that C psi of x, C inverse, which is psi conjugate of x, turned out to be minus I gamma 2 alpha NC psi star of x. Star meaning you adjoint the operators, complex conjugate the numbers, and you don't twist them around. And as I said, we have this particular relation. So I see that Ms. Blasio is here, and so I will indicate a bit. Something about C, P, and T, and then Feynman's propagator, and then E plus E minus goes to mu plus mu minus. Okay, that's one of the simpler QED calculations. For the parity, it's pretty much the same except for a different phase. So we have P A dagger PSN, P inverse is some other phase. I'm going to call it beta N A dagger. And this is, if I'm talking about P vector, then it's minus P vector Sn, and PA PSN P inverse is beta N star of minus PSN. And then for the antiparticles, we have the same thing with just N replaced by NC. And the rule then is that alpha NC has to be minus alpha N star. And in that case, we arrange that P psi of x and t, P inverse, is then this phase beta n gamma 0 and then psi star of minus x and t. And I'm a little puzzled. What is it? Psi star? I think that must be a typo because under parity we're not. Yeah, I think this must be a typo. So I better check that in the notes. Let me just say a couple of words about time reversal. In time reversal, as I said, it's a very spooky business because the time reversal operator, I really should have discussed this on Halloween. The time reversal operator is antilinear and anti-unitary. And what we mean by that is that t on some state phi, t on some state psi is phi psi complex conjugate, which is psi phi. So it's normally, if this were unitary, you'd say that this was that without a star. We get a star. And moreover, t on a linear combination of two states, well, I called it A and B in my notes, is Z star T on A plus W star T on B. So this is something that we don't come across normally in physics classes or even in linear algebra classes. On the creation and annihilation operators, what we have is something like this. T inverse gives us some phase. If I use beta there, I'll have to use gamma here. I think I won't use gamma, I'll use C to avoid confusion. C sub n, and then a strange thing, minus 1 to the j plus j minus s, a dagger of minus p minus s and n. So of course the spin is reversed, momentum is reversed, and this is just free momentum. And T A of PSN, T inverse is then Cn star minus 1 to the j minus s, A minus p minus s, n, and on antiparticles we have T A dagger PS and C, T inverse is, okay, let me get this straight. It turns out to be Cn star minus 1 to the j minus s, a dagger of minus p minus s and nc, and T on A of p and s and nc, T inverse is Cn minus 1 to the j minus s minus p minus s nc. Okay. All right, and causality here requires that C sub nc be C sub n star. All right. The T on a Fermi field gives you a phase factor times gamma 5, gamma 2, gamma 0 times the field at minus t and x. All right, so much for that. Now, questions? Of course, CPT is an invariance of quantum field theory.
I have a question.
Yes.
So, was CP at some point an invariant of quantum field theory? Then they
You mean just CP?
Yeah.
No, people thought it was for a while, but in, I don't know, I think it might have been 64 or so. I think his name was James Cronin, and some others at Chicago and other places showed that CP was not invariant. I think they were doing experiments on K mesons.
So was it predicted by quantum field theory that it wasn't going to be?
No. It was, well, I mean, let me give you the sociology. Actually, here, I have to give you a handy. Oops. And also the TA. Did anybody else ask a question? Originally, back in, say, the 50s, or the early 50s, people were convinced that P, C, and T were all invariant to the quantum field. And then Yang and Lee pointed out that this wasn't by any means clear in the weak interactions, and it had to be settled by experiment. Experiments were done, and it turned out that parity was not invariant under the weak interactions. And in fact, the absurd thing is that it was maximally violated. I mean, it was about as broken as could be. And that's, of course, not, I mean, it's understood mathematically, but what's going on is not really understood. In other words, why is it broken in the weak interactions? Okay. And then they thought that CP was invariant, but about 10 years later, it was shown that CP was not invariant. We're still clinging to the belief that CPT is invariant, and that may or may not be true, because quantum field theory may not be fundamental theory of nature. In that case, it may be that CPT is not considered. Okay, one of these things that's suspect about all of these discrete symmetries is that they're not gauge symmetries. So they don't add that much symmetry, and so losing them doesn't really mean that much. Okay, the symmetries that are important are the symmetries that are gauge symmetries, where you can do things differently at different points in space and time, and still the action's invariant. And those are the symmetries that require the interactions of the standard model, or interactions like those of the standard model, the strong, the weak, the electromagnetic, and the gravitational interactions. So those symmetries are of a different kind from the reflection symmetries. I mean, compared to the symmetry of electrodynamics, parity is kind of trivial. It's just, you just flip and then you flip back, and it acts the same way on every point in space and so forth. So it's kind of, it's not a very profound symmetry. Okay, we were talking about Feynman's propagator, and I had not quite finished. And as I said, I think that Schwartz is a little bit sloppy, so I'm a little hesitant as to how much to do, because I don't want to take up too much time here. I think I sent you the whole thing as a PDF. Yes.
Is there a reason those aren't posted on the website?
I'm sorry, say it again?
Is there a reason those aren't posted on the website?
Is there a reason I haven't put these on the website?
Yeah.
Yes, stupidity on my part. Together with a little bit of laziness. It occurred to me this afternoon
but I thought, gee, all right, I will put them on, promise.
Thank you.
Yes.
Speaking of the website, you're not going to take the video of the lectures down, are you? Anytime soon?
No,
Okay.
no, I
You
tend
should
to
get a
basically
YouTube
leave them
channel.
up permanently, huh?
Yeah.
You should get a YouTube
Yeah,
channel.
why?
Yeah. Yep.
Yeah, I generally just leave them up, and,
You should do it, like, do it.
No, I can't.
Why?
It's not my video.
Do you have a
Well-
Gmail address?
have what?
A Google email account?
Yeah, I have a Google email.
Yeah, so you can set up a YouTube channel and then put all of your videos up there, and then that would be a convenient place for people to find them.
All
And
right,
watch them on
well,
YouTube.
why don't we talk about it after class?
Okay.
Okay, now, the field psi of x, of course, is the sum on the two spins integral dqp 2 pi cubed square root 2 omega p, and then we have u of p and s, a of p and s, e to the minus I px. And now to make things a little bit simpler, v of p and s, and I'll use b dagger of p and s, e to the I px. So that's basically, that's the field, and then the Feynman's propagator is the time-ordered product. And to make the notation simpler, I'll follow Schwartz and use 0 and x. And this is then theta of minus t, 0, psi of 0, psi bar of x, 0 minus theta of t, 0, psi bar of x, psi of 0. Vacuum. Okay. Notice there's an extra minus sign. It's not just the time-ordered product. There's an extra minus sign, and that's to make the thing smooth as t goes from negative to positive. If we didn't, we'd have an abrupt change there. And if we have psi 0, psi j0, psi bar L of x 0, let me just flag a typo here. I'm going to skip one step because I did much of this last time. That's d cubed p 2 pi cubed square root 2 omega p d cubed q 2 pi cubed square root 2 omega q. Actually, let me skip several steps here because how slow should I go?
How slow do you want to go?
I don't care. I want to go as slow as you want me to go.
And could you write it all out?
Huh?
Could you write it all out?
Yeah, it's all here. Well, all right, since I started writing this, yeah, all right, let me skip a couple of steps. And what we have is this, and then we have the sum uj of p and s, u bar L of q and s prime, e to the alpha qx, 2 pi cubed, delta p minus q, delta s prime. Okay, so that's what we get for the first term, putting in explicit indices. And now, the delta function obviously helps us out, and then what we have is integral d cubed p over 2 pi cubed, 1 over 2 omega p, and then a sum on spins uj of p and s, u bar L of p and s, e to the I px, and this gives us d cubed p, 2 pi cubed, this is an identity. The sum over S of the spinors is P slash plus M. The JL matrix element, 2 omega P e to the I px. Okay, and the second term is 0 psi L bar of x psi j of 0 vacuum. And this, I'll just go right to the end. It's 2 pi cubed in the denominator d cubed p. And it's because it's a V's, because it's the spinors for the antiparticles, it's p slash minus m jl over 2 omega p e to the minus I px, and the minus sign is because of the antiparticles. Now we have these heavy sign relations, e to the I omega p t, theta of minus t is I over 2 pi integral minus infinity plus infinity e to the I p0 t over p0 minus omega p minus I epsilon dp0. So I'm writing it differently from the way that Schwartz wrote it. And this one is I over 2 pi integral e to the I p0 t over p0 minus omega p plus I epsilon dp0. Okay, so the propagator, basically we put all this together and we have a time-ordered product psi j of 0 psi bar L of x. And I won't, obviously the next thing is the second line on board 2, and what this gives us then is theta of minus t integral dqp 2 pi cubed p slash plus m over 2 omega p jl e to the I px minus theta of t dqp 2 pi cubed p slash minus m, again jl, divided by 2 omega p e to the minus I px. Okay, so you see there are many common factors in those two integrals, and what we have to keep in mind, though, is that this p slash is the p slash from the spinors, and consequently it's an on-shell p slash. So in other words, p slash is omega p gamma 0 minus p dot gamma. That's why over here I did an integral over p0 and made the omegas explicit. And so this propagator then, so let me just put this aside so that I can write equals theta of minus t integral dqp 2 pi cubed omega p gamma 0 minus p dot gamma plus m, and it's JL, but I don't think I need to write that every time. And then it's, this thing is an on-shell p, so this is e to the I omega t minus I p dot x minus theta of t dqp 2 pi cubed omega p gamma 0 minus p dot gamma minus m over 2 omega p, and the phase factor here is e to the minus, well, maybe I should write it explicitly,
e to the minus I omega t plus I p dot x. And that omega is omega p, so maybe I should have put p there. Okay. So we can now insert the formulas for the Heaviside functions. And notice what we've got is is theta minus t e to the I omega pt, which is the left-hand side of the first equation. And then we have minus theta of t e to the minus I omega pt, which is the left-hand side of the second Heaviside equation. And so this thing is then d cubed p over 2 pi cubed 1 over 2 omega p. I think maybe I'll just leave that by itself so as not to write it twice. And then what we have, well, all right. Omega p gamma 0 minus p dot gamma plus m. And this is times e to the minus I p dot x. And then it's I over 2 pi integral e to the I p0 t over p0 minus omega p minus I epsilon dp0. And then the other term is omega p gamma 0 minus p dot gamma minus m. And I over 2 pi integral e to the I p0 t over p0 minus omega p plus I epsilon dp0. All right, well, that's a big load. What we do over here, though, is we flip the sign of p vector in the second integral here. So there was I left out there was an e to the I p dot x that I forgot to put in. So we have e to the minus I p dot x, e to the I p dot x, so we want to flip those. So when we flip p in the second integral, we get a sign change here. We get the same sign as there. The p0 doesn't change, p0 doesn't change. And so the only change basically is that. And so then effectively what we have, if we combine the d cubed p with the dp0, we have a d4th p. We combine the 2 pi's. And so what we have then is integral d4th p over 2 pi to the 4th, and then we have omega p gamma 0 minus p dot gamma plus m over 2 omega p e to the I. Now once we flip the same signs there, we have the same e to the I px. So we just have e to the I px, and now this is Lorentz px. So it's p0t minus p dot x. And what do we have? Oh, nuts. I should have, here, let me take advantage of erase this. E to the I px, Lorentz, okay. And then what we have is this first term times I over p0 minus omega p minus I epsilon
And then the second term is omega p gamma 0 plus p dot gamma, because this sign flipped, minus m over 2 omega p, and then I over p0 minus omega p plus I epsilon. Okay, so that's what we've got. And now comes the really hard part, which is the high school algebra. Yes.
Actually, can I ask an even more naive calculus question?
Yeah.
In what sense does it make sense to take these variables, which are outside our integral, and then push them through the integral, change their sign, and then pull them back out?
Goodness.
It seems like that's essentially what we did.
All right, well, I didn't really mean to, which specifically?
Well, in this second term here, right, how we go from p vector to minus p vector.
Oh,
Yeah.
okay. Well, all right, well, it's easiest if we just look at the thing when it's isolated here.
Yeah.
Oh,
okay.
And there, we just have an integral dqp. This is a three-dimensional thing. This doesn't depend upon the sign of p vector. And so if we just flip p vector, we get the minus there, and we get a plus there. That's all. All right. Here, let me.
No, thank you.
Well, you can
Well,
charitably pass it to
Thanksgiving
one of
is
your
coming up.
starving fellow graduate students.
The second week I hit it.
It is essentially.
Okay, I'll write down the high school algebra. Because it's high school algebra, I'll skip a step.
There's going to be a quiz afterwards too.
No, I'm not big on quizzes.
High school algebra.
That's from the high school you went to.
Okay, and what we see here is we've got two different things going on. We have the omega p times this funny denominator, and the omega p gamma 0 times a different funny denominator. But then we have minus p dot gamma times the denominator, and then plus p dot gamma times the denominator. So there are two separate terms there. And this one is 2p0 over p squared minus m squared plus I epsilon. The other piece of high school algebra, well, it's what happens when there's a minus sign here. So I'll just write minus. And then it turns out to be 2 omega p over p squared minus m squared plus I epsilon. And that's the one that contributes if you have minus p dot gamma. Okay. If you now combine all of that, what you have is the Feynman's propagator, psi k of 0, psi bar L of x is I integral d fourth p 2 pi to the fourth e to the I px, and that's Lorentz. And then we have omega p gamma 0 over 2 omega p 2p0 over p squared minus m squared plus I epsilon plus minus p dot gamma. I'm saying here plus m. Yeah, you see the sign of m also flipped. And we get then 2 omega p over, okay, and for matrices it's JL. And now what you see happens here is that the 2 omegas cancel. this omega and the two omegas cancel again. And so what we have then is p slash plus m over p squared minus m squared plus epsilon, sorry. And so this thing is I integral d4th p 2 pi to the 4th e to the I px p slash plus m, and now I'll put in the indices JL over p squared minus m squared plus I epsilon. And one can also, well, instead of writing it in a different form, let me now go to x and y, which is what one normally uses, and then we have psi j of x, psi bar L of y, and here I'm replacing x by y minus x and then translating by x. That's how you get to this. And you wind up with d4th p over 2 pi to the 4th e to the I p y minus x I p slash plus m JL over p squared minus m squared plus I epsilon. And you can also write this as d slash plus im JL on integral d4 p pi to the 4th e to the I p 1 minus x 1 over p squared minus m squared plus I epsilon. Okay. And so that's what I've got. Okay, now let's suppose we turn then to a QED problem, and it will be E plus E minus goes to mu plus mu minus. So I'm going to start over here. Well, maybe I'll say a couple of things. So we're talking about E plus E minus goes to mu plus mu minus. And let's remember what the action density is. It's minus a quarter F mu nu, F mu nu, plus I psi bar, well, let me do it this way. I du minus m psi, and then minus E psi bar A mu gamma mu psi. So this is the interaction Lagrangian, this last bit here, and this is just the free action for the spin 1/2 particles, free action for the spin 0 photons. And so then what we'll be talking about is basically P3, P4, S, P1, P2, and this is going to be two annihilation operators, say AP3, P4, and then E to the, and it's going to be minus I times, or I times the interaction Lagrangian, which is minus I E integral A mu psi bar gamma mu psi d4th x, and of course this is time ordered. And then we'll have out here
A of P1 dagger, A dagger of P2. And actually, I left out a product of square root of twice the energies because the states have a square root of 2e and time, and then the creation operator, and then the vacuum. Okay, and we have the same field. The field is the same field that's in the top line of board 2. And let's see, I have a little bit more space here. Remember that a dagger, then the commutator here is a delta of spin, delta of momentum, and then 2 pi cubed. Okay, so this thing 3, 4, S, 1, 2 is then going to look like this. 0, A4, A3, time-ordered product, and we're going to be expanding. Yeah, Schwartz does this by just saying, well, here are the Feynman diagrams, and bingo, here's the answer. I'm going to actually try to derive it for you so that, because I think that actually, if you're doing a real calculation, the derivation that I go through is the easy part of the calculation. The hard part in some of these calculations is when you try to do some of the integrals. Of course, then I'm speaking actually of how it was when I was a graduate student, because we didn't have Mathematica, we didn't have computers. And so you actually had to do these integrals using Feynman's tricks and your fingers, and sometimes your brain, but mostly the fingers. Feynman's tricks. Anyway, so what comes down here in second order then is going to be sidebar A slash psi at x, sidebar A slash psi at y, and there's going to be yes. Yes. Fine. Okay, so there's a minus e squared over 2 because we're expanding this thing, this exponential, to second order. We need 2 vertices for the thing not to be 0. And so then, once again, we have what? A1 dagger, A2 dagger, 0, product square root of 2e's. And the product is over all the all 4 particles. Now, what we always do, you see, is say, well, we're going to have, let me draw the Feynman diagram in this case. It's electron in P1, P2 is positron in, photon across, P3 is muon out, P4 is anti-muon out. So this is E, this is E plus, this is E plus. So this is the Feynman diagram. And we can choose, if we think of this as a space-time diagram, we can say this is X and that's Y. And I think the way I did it then was to say Y, X, I'm going to call this one X, and that one Y. And in that case then, the field psi at X is going to stop the incoming electron, and
psi bar is going to stop the incoming positron. And so what this, and factor 2 is canceled because we chose x to be this vertex. And so we have minus e squared a4, a3 time ordered product, and of course this is an integral d4 of x, d4 of y. Time ordered product psi bar a slash psi and y. And now what happens here is we get a v bar of, I was using two different notations, of P2, and I'll suppress the actual a slash of x, u of P1, I'll suppress the spin, e to the minus I Px, e to the P1 x, e to the minus I P2x. And then what's left is just the vacuum and the square root of 2 e's. Actually, 2 of the 2 e's just went away because they cancel 1 over square root of 2e in the denominator. So this is square root of 2e3, 2e4. That's all that's left at this point. Well, here the psi bar is going to create the outgoing muon, psi is going to create the outgoing anti-muon, and at this point what we have is minus e squared 0 time ordered product u bar of P3 a slash y, we're integrating of course, v of P4 e to the I P3y plus I P4y e to the minus I P1x minus I P2x, and then we had here v bar P2 a slash of x u of P1 vacuum, and all the square root of these are gone at this point. And let's recall what the photon propagator is. 0 time ordered product, a mu of x, a mu of y, 0 is, and in all its glory, it's 2 pi, d4th p over 2 pi to the 4th, e to the I p x minus y, minus I over p squared plus I epsilon. And now if we do this in the most general of the gauges that we're talking about at least, actually I'm going to use k instead of p because we've got p's and q's already, but we've got too many p's. So d4th k, e to the I k, k squared, and now this will be k nu over k squared. Okay. All right, so that means, you see what you've got here is vacuum, a gamma and an a mu, a gamma and an a nu, or gamma nu and an a nu. And so what we've got here then is minus e squared integral d4th x, d4th y, and of course I forgot them again, d4th x, d4th y. d4th k over 2 pi to the 4th, and then we have u bar p3, and let us say, okay, gamma mu v of p4
And now what's left is the propagator, and so that's minus I over k squared plus I epsilon, and then this eta mu nu minus 1 minus c k mu over k squared. And I left out the overall phase factors, it's e to the I y P3 plus P4 minus Ix P1 plus P2 e to the I k x minus y. All right, I think I've got everything at this point. And now the integrals over space and time give us these marvelous Dirac delta functions, which then simplify everything. And so what happens? Let me let's see. If we first say do the integral over x, then we have a p1 plus p2 here, and then we have a k. Well, that sets k equal to p1 plus p2. Okay. Then what we have is a y integration. Well, we do the k integration and it's gone, and the 2 pi to the 4th goes. Then we have the y integration, and that gives us 2 pi to the 4th and overall delta function of momentum. So what we're going to get then is minus e squared 2 pi to the 4th delta 4th of p1 plus p2 minus p3 minus p4. So that whole stuff. And then this u bar p3 gamma mu v of p4 v bar p2 gamma. Well, there's eta mu nu, and so this eta mu nu just raises the mu and nu and makes it an upper mu, and then u of p1, and then we have minus I over p1 plus p2 squared, and this is, we can forget about the I epsilon, but I haven't done these terms yet. I want to show you that these terms are 0. And let me just, so I unfortunately skipped a lot. So in other words, this propagator minus I over p1 plus p2 squared is really has all of this stuff in it. So let's see why those things are 0. And the reason is basically this, that we have, for example, let me just, all right, let's do one of them. Let's do the V bar. Well, which one was P1 and P2? Okay, V bar P2, and then gamma nu, and then we would have P plus Q nu U of P1. Actually, it's P1 plus P2. I was using 2 different notations when I wrote this up. I started out with my notation, which didn't have any subscripts, and then I switched. Okay, so this is, if we take, say, the K nu. K nu is P1 nu plus P2 nu, and that goes, that is contracted with the gamma nu here, V bar P2 U P1. Okay. Now we can rewrite this as V bar P2, and then gamma nu P2 nu is P2 slash U of P1, and then plus V bar of P2, and now this is P1 slash U of P1. Well,
the Dirac equation of momentum space is that P slash on U of P is minus M U of P. And when you take the adjoint and have a gamma 0, and well, it's acting on the V, you get a plus M. And so this turns out to be M V bar of P2 U of P1 minus M V bar of P2 U of P1, and so that's 0. So in other words, these extra gauge fixing terms don't contribute, and because they shouldn't contribute, because otherwise you'd have a cross-section dependent upon some arbitrary parameter C, and you certainly don't want that. And it's nice to see them go away. Once they're gone, though, our amplitude is just this rather simple, well, compared to some things, it's a rather simple. It's of course not really very simple. All right. So now, I'm going to switch back to Schwarz's notation and follow him fairly closely now. Are there any questions? Wow, I used a very, very, very wet eraser. So it'd be good if someone had a question until the board dries. Yes?
No, thank you. Do you think they'll ever invent self-cleaning chalkboards?
Yeah. I was thinking about that.
I don't know. I mean, I think you could probably make them, right? Because you just have one vibrate and it would shake off the chalk, maybe. No?
I mean, if you had an electric chalkboard or a digital chalkboard.
Hmm?
If you had a digital chalkboard, right, that might work. You just press a button and
Yeah.
the feel is not there.
Yeah.
We should make chalkboards out of the same touchscreen stuff that they make iPads and iPhones out of.
Oh. And so you still have that like gritty feel?
No, then you can just use your finger.
It's
Actually, while we're at it, why don't I erase this board also?
What would be so expensive?
You realize that the cost of technology tends to increase as time goes by.
It doesn't matter, it's still expensive.
I think everyone buys an iPhone these days, even though they came out at $600 a pop back when they were first introduced.
Okay, an iPhone screen, if it's $600, you can run a new iPhone screen to make a whole chalkboard. Not just one chalkboard, but a whole
right.
It's just
chalkboard.
economies of scale.
Yeah. Where everyone could just get smarter.
Well, all right, so what are we going to do next? Let's take that formula and write down what the matrix element is. So in Schwarz's notation, then this is E squared over S. Remember, S is P1 plus P2 squared, and that's what we had in this expression. And then we had, put my reading glasses on. We had V bar of P2, gamma mu, U of P1, U bar of P3, gamma mu, V of P4. Okay. So that's, boy, it's amazing how low the humidity is in New Mexico. That is especially true in the winter. It's not yet quite winter, but once they start turning up the heat, I'll be able to erase boards all the time with the wet eraser. Okay, gamma mu dagger
gamma 0 is what? Well, it's gamma 0, gamma mu, and gamma 0 dagger gamma is gamma 0. So the gamma 0 is Hermitian, of course, and the other ones are anti-Hermitian, but they anti-commute with gamma 0, and so we have this relation. What that means is that if we have something like psi 1 bar gamma mu psi 2 dagger, then, and this is part of the reason why we have this bar notation, it's that this is psi 1 dagger gamma, in Schwarz's metric, of course, whether you have gamma 0 up or 0 down doesn't matter. And so this is, although I find it a little bit annoying to have one up and one down without any reason. So let me just do this. So this is psi 2 dagger, gamma mu dagger, gamma 0 dagger, psi 1. And this is then psi 2 dagger, gamma 0, gamma mu, psi 1, and that is psi 2 bar, gamma mu, psi 1. So in other words, this thing, psi 1 bar, gamma mu, psi 2, you take the adjoint, it just turns into the same thing with 2 and 1 interchanged. And so the adjoint of M is M adjoint, and then this is E squared over S, and it is then V bar P4 gamma mu U of P3 U bar of P1 gamma mu V of P2. Okay. And so the absolute value squared, which is what we need in order to, by the way, this thing is a number, okay? This is a complex number.
Thank you for clarifying. I was a little bit confused.
Right. What happens is you've got a vector index, I mean a spinor index contracted with this spinor index, and then another spinor index here with that one. So that's this is a number, this is a number, that's a number, and two numbers make a number. Okay. So what is M squared? It's e to the fourth over S squared, and it's then V bar P2 gamma mu U P1 U bar P3 gamma mu, gamma mu V of P4 times V bar of P4 gamma mu U of P3 U bar P1 gamma nu V P2. All right. Notice we switched from mu to nu in the second term because we're summing over mu here, we're summing over mu here, and so just not to get them confused, we call one of them nu. All right. Now, one of the remarkable identities that I derived, at least in the notes which I sent to you on spinners, the spinner notes, and which out of laziness and stupidity I forgot to put on the web page, which I will put up there soon. What we have is the sum of V of, let us say, P4, V bar of P4, and now S. So I'm putting S back in. I suppressed what the spin index was. If we sum over S, what does this give us? Well, it gives us something quite nice. It gives us P4 slash minus M. And in this case, it's M muon, because these were muons. And
remember when we make the spinors, it's basically P slash plus or minus M acting on the basic spinors at momentum 0, which we have to take from Weinberg. And the other relation is sum on S, U of, let us say, P3 in S, U bar of P4 in S, summed over S, is P3 slash plus M mu. Okay. The thing I was, I lost track of what I was saying. It's the spinors then, you take the spinors at 0 and you multiply by P slash plus or minus M to get the spinors at non-zero momentum. The M there is the M that's relevant for the particle, and so in this case, the final state particles, the M you use is mu1, and in the other case you use, for the initial state particle, you use m-electron.
So your U bar momentum is at P3?
These both are the final state. Yeah, sorry about that.
Okay.
Great. Okay, you get 2 candies for correcting a mistake. Oh, sorry. Okay, so what do we do here? Well, what we do is we take a sum. In fact, let me just say one thing, 2 things. If we had an experiment in which we selected the spins of the incoming electron and the incoming positron, and we measured the spins of the outgoing electron, outgoing muon, and the outgoing anti-muon, then we would have this as our amplitude, and that would be it, and we'd have to compute what that is. And computing what that is a little bit hairy. Okay? I mean, it's not impossible, and of course, I guess there are computer programs that, certainly there are computer programs that do it. But in most experiments, you don't measure the final state spins, and you have no idea what the initial state spins are. And in fact, you assume, I think quite correctly, that they're half the time spin up and half the time spin down. And so what we do is we just sum over these spins. And now what we have is U bar, P3, S prime, gamma mu, V, P4, S, V bar, P4, S, gamma nu, where am I? U of P3 S prime. Okay. So that's what? That's sort of, it's not the whole thing, it's just part of the amplitude. So this part would be what? It would be U bar. It will be this part. So this is the part that we're doing here. Okay, it's the middle part. And all these things are numbers. Okay, so that's the part that we're looking at. And so what do we get? Well, what we get, doing the sum on S, V bar, we have then U bar P3, gamma mu, and then this is P4 slash minus M muon, gamma nu, U of P3, S prime. And now we can equally well put the, take this U and put it here, and then we have a sum over S prime. Oh, this is an S prime. So So we take, all right, let me just do it explicitly. Sum over S prime U of P3 S prime U bar P3 S prime gamma mu, and then the left P slash minus P4 slash minus mu gamma nu. Okay, then summing on this, summing on S prime gives us another P slash, and so what we wind up with here is that this is gamma mu P slash, actually what I did in my notes now that I think about it is instead of moving this guy forward, I moved this guy back. And in that case, what we get is gamma mu P4 slash minus mu gamma nu P3 slash plus m. So that's what that sum is. It's a product of these gamma matrices. But it's, if we keep track of the indices, and so let me do that now. So I'm going to put in the spinor indices, beta, delta, delta. So that's a number, okay? And then over here, we have, I'll put in alpha, epsilon, epsilon, okay? So now this thing is U bar beta. Well, it sounds like Barbados, doesn't it? U bar beta, gamma mu beta delta, and now this P4 slash minus m delta alpha, alpha epsilon, epsilon is what we've got. Okay. And now what I chose to do was pull the epsilon, pull this one forward, but if I'm going to do things so that I connect with that, let me instead move the U bar forward. So we have here U epsilon P3 S prime, and then U bar beta P3 S prime. So that's what it looks like, whereas this guy is to the right over there. I'm just worried. What did I? Yeah, and this one is gone then. I keep erasing with this horrible eraser. Okay, and then, but what is left here? This is a beta delta, and this is delta alpha. So beta delta, delta alpha, gamma was alpha epsilon, epsilon, and then beta. So you see the thing is actually a trace. So in other words, this was beta delta, delta alpha, alpha epsilon, epsilon beta when you take the sum over S prime of U bar and replace it with P3 slash plus M. So this thing is actually just the trace of gamma mu P4 slash minus mu gamma nu P3 slash plus mu period. And of course the trace is cyclic, so you could take this one and put it there if you want. The rest of this thing gives you another trace, and now what you do is you average over the initial spins and sum over the final spins. There are 4 possible initial spins, up, down to the electron, up, down to the positrons, and divide by 4. So the total thing then we have to compute is 1/4 sum S prime of this m squared. And this gives you e to the 4th over 4s squared, because we've squared the thing, and a product of 2 traces. And the first trace is P1 slash plus me gamma nu P2 slash minus ME gamma mu. So that's one trace. And the other trace is P3 slash plus mu gamma mu P4 slash minus mu gamma nu. So that's the expression. What's the time situation? All right, well, apparently we've run out of time. All right, well, I will just continue this next time. It's your homework, which I assigned, was probably due last Wednesday, is to compute things like this. And so this is basically the trace of 4 gammas. And there's a standard formula for that involving a bunch of etas. And if you apply the two of them, you then get a suitably simple formula. And if you go further, then what you get is a nice formula for the cross-section. And I'll go through the rest of that on Wednesday, if today is Monday, or on Monday if today is Wednesday. Any questions? All right, I guess we can start.